Hi, this is Mrs. LaBarbara. This is Physics Chapter 8. Today's topic is electric field between parallel plates and inside a conductor. Objectives are: know the property of electric field between parallel plates. Know the conclusion of Millikan oil drop experiment. Know the property of electric field inside a conductor. Understand, a charged object placed between two charged plates will experience the same force no matter where they are placed, and it will accelerate toward the oppositely charged plate at a constant rate. The rate of acceleration will depend on force and mass. Be able to determine the strength of electric field, force on a charge, or amount of charge using electric field equation. Be able to sketch diagrams of electric field of parallel charged plates, and be able to determine the rate of acceleration for charged objects inside the electric fields. Be able to explain the reason for lightning to happen. Be able to sketch the path of a charged object as it moves through an electric field. Fields between two oppositely charged parallel plates. If the distance separating the two oppositely charged parallel plates is small compared to their area, the electric field between the plates is uniform. That means the electric field on top is the same as on the bottom, is the same around in the middle. The field lines are from positive plate to the negative plate. Since F equals E times Q, the force on a charged particle is the same anywhere inside the plates. A charged particle entering the field will accelerate toward the plate with the opposite charge in parabolic path. For example, the positive will accelerate toward a negative plate, the negative charge will accelerate a positive plate, like this. Example: an electron moves between two charged parallel plates from point B to point A as shown in the diagram. The force of the electric field on the electron will remain the same. This is because the field is constant and Fe equals to E times Q. Since E is the same, Q is the same, the force has to be the same. Another example, in the diagram, proton, neutron, and electron are located as shown between the two oppositely charged plates. The magnitude of acceleration will be greatest for which particle? So here is the parallel plates. So one thing we know about parallel plates is the electric field is uniform. Since the electric field is uniform, the force on proton and the electron has to be the same because protons and electrons have the same charge. On the other hand, the force on the neutrons is zero because neutron has no charge. Now, since acceleration is net force over mass, force on the proton is the same as the force on the electron. Acceleration will be greatest on electron because the electron has smaller mass. Millikans oil drop experiment. In 1909, Robert Millikan performed an oil drop experiment to measure the elementary charge. The experiment entailed balancing the downward gravitational force with upward electric force on tiny charged droplets of oil suspended between two metal plates. So basically, he sprayed the oil droplets into this, under the cover into that container, and there is a gap between the top plates, and some oil drop will be entering this electric field. So he observed oil drops that suspended between the two fields. When the oil drop suspended between the two plates, that means the forces are balanced. The gravity equals to electric force. And from here, he can figure out the charge on the oil drop. What he found out is that there is no drop with a charge less than 1.6 times 10 to the negative 19 coulombs. So that's an important number. I hope you recall that number. The charge on other drops will integral multiples of this value. That means the other charges can be 3.2 times 10 to the negative 19, 4.8 times 10 to the negative 19, and so forth. This finding demonstrated that there is a smallest possible charge, and we call this elementary charge. 1e equals to 1.6 times 10 to the negative 19 coulombs. So we have learned this before. I've just told you this is the elementary charge, and this is because Millikan had found this to be the elementary charge. This is a charge on a single proton or a single electron. Take a look at this example. What did Millikan conclude after performing his oil drop experiment? So we just said he concluded there is an elementary charge. So oil drop may not have a value less than this amount, 1.6 times 10 to the negative 19. On the other hand, also all the charges on any oil drop is integral part of this charge. So the answer is number 3. Another example. Seeing a diagram which illustrates Millikan oil drop experiment shows a 3.2 times 10 to the negative 14 kilogram oil drop with a charge of negative 1.6 times 10 to the negative 18 coulombs. So the oil drop was in equilibrium when upward electric force on the oil drop was equal in magnitude to the gravitational force on the oil drop. So what was the magnitude of electric field intensity when this oil drop was in equilibrium? So when a drop is in equilibrium, the forces has to balance. Electric force has to be equals to gravitational force. Electric force is E times Q, gravitational force is M times G. So from here, we can figure out E equals 2.0 times 10 to the 5 newtons per coulomb. Negative indicated direction, so the magnitude is just 2.0 times 10 to the 5th newtons per coulomb. Another example, an object with a net charge of 4.8 times 10 to the negative 6 coulomb experience a force has a magnitude of 6 times 10 to the negative 2 newtons when placed near negative charge and metal sphere. Now this question has 2 parts. What's the magnitude and the direction of the electric field strength at this location? To figure out the magnitude, we use the equation E equals to F over Q. So this is the magnitude, 1.25 times 10 to the 4 newtons over coulomb. To find the direction, we have to look at the charge created this field. The charge created this field is a negatively charged metal sphere. A negatively charged metal sphere will produce a field toward itself. So the field is directed toward a sphere. Electric field and conductors. So conductor, we learned, is a material which allows electrons to move freely inside. So a charged conductor will distribute its charge on its surface. It does this to reduce the repulsive force between the charge. So eventually the force between the charge becomes 0. When this happens, the charge doesn't move anymore because the force equals 0. Then when this happens, we say the conductor has reached a state of electrostatic equilibrium. So there are 4 properties associated with a conductor in electrostatic equilibrium. The first one is electric field anywhere beneath the surface is 0. This is the principle of shielding all electrical equipment. So that's why we have a metal case around your iPhone or any cell phones or any other electric device. You have a metal case around it. So to prevent it to be damaged by any electric field. Another property is all the excess charge on the conductor is outside on the surface of the conductor. And property number 3 is electric field has to be perpendicular to the surface. And property number 4 is electric field are strongest at locations along the surface where the object is most curved. Here are some pictures of the field around the conductor. The first one is the shell. So the shell has a thickness, so the charge are distributed outside and inside. So inside the shell is empty space. In that empty space, electric field equals to 0. So this is the principle we use to protect our electrical equipment. The other examples, even a metal sphere has absolutely charged charges on the surface of the sphere. All the charges on the surface of the sphere inside E equals to 0. This is oddly shaped metal sphere, metal, and we can see all the charges are distributed outside. And all the field are perpendicular to the surface at each point. Another thing is the most curved part has strongest field. So over here, the field is strongest. Over here is the second strongest. The field is weakest on the flat surface over here. Let's take a look at this example. A metallic sphere is positively charged. The field at the center of the sphere due to this positive charge is 0. Now let's talk about lightning. A precursor of any lightning strike is polarization of positive and negative charges within the storm cloud. So on the top is positive, on the bottom is negative. When a thundercloud is passing over the ground, especially when it's lower, this negative charge is going to push the negative charge in toward the ground, inside, toward down more. So on the top of the surface, you'll have a positive charge. So sometimes if you go outside in a very, very cloudy day, you may feel a strangeness in this case. This is because there is electric field between the clouds and the positive charge on the surface. And this field is kind of like a parallel plates. So what happens when the clouds is very close to the ground, the charge is experiencing a force, and that force will move the negative charge toward the positive charge on the ground. And the positive charge will move up, and negative charge will move down. When they meet, you will see a path. A path will be formed, and this path is a lightning. So the enormous and rapid flow of charge along this pathway between the cloud and earth heats up the surrounding air, causing the air to expand rapidly. And this expansion of air will create a shock wave, which we observe as a thunder. So we use lightning rods to protect our homes. So tall buildings, farmhouses, and other structures susceptible to lightning strike are often equipped with lightning rod. Lightning rod is kind of like sharp object. This sharp object will have tremendous electric field around it. And when lightning happens, instead of striking the whole house, because over here you have the tremendous amount of electric field, the lightning will come to this point, and that you will need a metal copper cable to conduct this to the ground. So to take the charge all the way to the ground. That's how the lightning rod protects your house. Lightning rod serves to safely divert lightning to the ground. In the event the cloud discharge its lightning via bolt. Here is check your understanding 2 questions. True or false? The presence of lightning rod on top of the building prevents the cloud with a static charge buildup from releasing its charge to the building. That's false. We know it has to release to the building. The lightning rod is to divert that charge to the ground. So the first one is false. The second one, if you place a lightning rod on top of your home but fail to ground it, then it is unlikely that your home will be struck by lightning. That is false. Your home will be struck by lightning, except now that the excess charge is not going to be diverted to the ground. It's going to come to your house. So in that case, the lightning rod doesn't really protect your house. It's false. That's it for today. Thanks for watching. See you next time.